Well, thank you for the organizers for inviting me. I was invited to give kind of an introduction to gravitational wave parameter estimation. In this room, we have several experts in that area, such as Alberto Vecchio, Ben Farr, Ilian Mandel. Hopefully, there are some graduate students, some people outside of the field that will get something from this, some people that are a bit new to this sort of thing, like Duncan, so they can maybe pick up a few things. I'm going to go through a few things, just a little basics on signal analysis, getting into some of the Bayesian inference, talking a bit about how we work in this area of Bayesian hierarchical modeling. I'm actually going to have some new stuff today, noise modeling. Everyone talks about signals and cares about signals, but most of what we get is noise, so it's very important to understand the noise, a little bit of how we go about this, and maybe I'll even get to some examples towards the end. All right. So we're talking about signals and additive noise. So you have your data, signal, and noise. This was just randomly chosen from the 14th of September 2015. So if you've got data is signal plus noise. If you do some complicated mathematics to rearrange this equation, data minus your model for the signal should just be noise, right? So you're looking to have after taking away your best estimate of what the signal might be, you want the residual to be consistent with noise. If you do not subtract off the signal correctly, then you're going to leave behind a residual that's not noise, as they like to do in Denmark. So what that tells you is your likelihood then is your probability distribution for the noise. So that defines your likelihood function because data minus your model should just be recovering. Your residuals should be consistent with noise. So if you don't understand your noise, then you won't understand if you've seen signals. And if your model for the noise is wrong, then you can bias your measurements of the signals. So it's very critical that you actually understand the noise. Now, most of the time, we take very simple models. I just said all this. We might take it being, say, stationary colored Gaussian noise, in which case we switch to the frequency domain. Actually, to a good approximation, LIGO noise is pretty Gaussian and pretty stationary, except when it isn't. I also work in pulsar timing. The pulsar timing case is dramatically harder than LIGO. The noise is very non-stationary. It's also not evenly sampled. There's all sorts of challenges, many different kinds of noise sources. So actually, LIGO has it easy. I think LISA will end up somewhere between those two extremes. So Duncan showed this earlier. Bayes' theorem. So here our likelihood is just our noise model. You then need a signal model. You've got a normalization factor, which is going to play the role of either a marginalized likelihood or an evidence. And then finally, you get your posterior distribution. And this is actually what you get directly. And this is posterior distribution on the waveforms. So for example, this is just an example from GW 150914. I will talk about this in a moment. Modeling the spectrum, modeling the signal as a sum of wavelets, and then you end up by computing a histogram essentially at each time, you get a posterior distribution on the waveform directly. So some analyses directly produce just waveform reconstructions as the primary product. You can have different kinds of signal models. So if you are able to do the calculations solving Einstein's equations, you might have, say, in-spiral waveforms, continuous waves, as Maria Alessandra was just talking about. You might have supernova-type, burst-type sources, which are getting better modeled, but still we wouldn't use them as templates at this stage. And then things like stochastic background. So all of these provide priors on our signal model, some of varying strength. So in the case of a template-based analysis, the prior is very strong. It's a delta function. It's a delta function that maps the signal onto some collection of parameters, such as the masses and spins, sky locations. So it's actually the very strongest kind of prior. And because the prior is the strongest, those are the most sensitive searches. As you gradually weaken your prior, your searches become less sensitive. With bursts, we typically work in the wavelet domain. So we're modeling the signals as some collection of wavelets and then some priors on where we put the wavelets. And for stochastic signals, we say they're a Gaussian, some kind of a Gaussian process with some kind of spectrum, right? So then you have maybe some priors on the spectrum. So how this works, level 1 inference is where you're just directly inferring the gravitational wave signal. So you have some model for the signal and the noise described by some set of parameters, and you actually just directly infer what the signal is from the data. And that's what things like the Bayes wave algorithm does, where you get these signal reconstructions. If you go to the next level, where you don't actually care necessarily about what the waveform samples are at every time or at every frequency, you can then marginalize over the signal, integrate it out, and then that is going to map you onto now just the parameters of the model. And then what you do is you use the marginal likelihood becomes the likelihood for level 2. So that's level 2 inference, which is what's done by, say, the Lau inference pipeline in LIGO. And then the next level, level 3 inference, you take something, you actually, if you don't care about your model parameters, you'd integrate those out, and then you get the evidence for the model. And that model evidence gives you, say, the odds ratios between models I and J, is just given by this posterior distributions on the models. So you've got your prior odds, so going in, which model did you think was more likely, and then the Bayes factor, which you get from the data, which updates your odds ratio. So that's actually model selection. Unfortunately, Will Farr, who is going to speak next, was unable to make it. He was going to talk on model selection, so he was going to be talking on this level 3 inference, but he couldn't make it. He's moving to New York. And the movers hadn't arrived or something like that. So just to go through a couple of concrete examples, if we take something like a template-based analysis, so where we have models like the ones that Alessandro Bonanno told us about earlier, where we have a mapping where we can actually predict the wave as a function of frequency or time in terms of some physical parameters, you integrate that out, it's just a delta function, and that just maps you onto then a likelihood that depends on the parameters, and then you go ahead and use that to do your inference, and that's where we get the standard. I'll maybe say a little bit about this. So to actually carry out this calculation, we use techniques such as Markov chain Monte Carlos, nested sampling to map out these distributions. And that leads to results like this, which we've already seen similar results today, where you've got the probability distributions now on the parameters of the model, such as the masses and spins. Another example of the kind of searches we do, if you have a stochastic background, you're not particularly interested in what the waveform is at each frequency because it's just some random variable. What you're interested in is the spectrum. So if we take a Gaussian likelihood for the likelihood function for the data, so that's the noise model here is just Gaussian. When you integrate this out, when you integrate out now the waveforms, you don't care about the waveform, or you care about is the spectrum, you do that, and this correlation matrix, which was just the noise correlation matrix, hopefully uncorrelated between detectors, except maybe there's some things that can correlate noise between detectors, but it's just a block diagonal matrix that's with each block is a different detector. Once you marginalize out over the gravitational wave signal, you get a new correlation matrix which has the noise component, but then it has a part that's correlated between detectors, big I and big J. And depending on which field you're working in, if you're working in LIGO, that's called the overlap reduction function. If you're working in pulsar timing, that's the Hellings-Downs curve, right? So this is now correlated between the detectors because it's the common response to the gravitational wave signal. And notice that it came from exactly the same likelihood that we use always. It's always the same likelihood. It's just what you do is you marginalize over the gravitational wave samples. And so this then becomes, we're just trying to recover the spectrum of the gravitational waves. An example of level 3 inference, a recent paper by Smith and Thrain in PRX, where what you do is you take the output of an earlier analysis where an evidence has been calculated for your signal model. They were talking about black hole mergers, and you've got the evidence for your noise model, and so those are the marginal likelihoods from your level 2 analysis. Then you have, say, a duty cycle, so they break the data up into M chunks. Each one is short, so the chance of there being a a black hole signal in there is quite low. And so the fraction of the chunks that actually contain mergers is this parameter psi here. And one of the nice things about this analysis is it combines not just the very confident detections, but also anything that's sort of sub-threshold. So you're just taking the evidence. Is it a 10% chance it's a signal? Is it a 1% chance? You just throw everything in. Anyway, you can then just change variables, integrate things out, and you end up with a likelihood that now gives you the merger rate. And so this kind of analysis is taking the evidence from the original kind of parameter estimation analyses that might be done, and then you combine that for all of the signals, and it's a way that actually they calculate in their paper that as a way of detecting, if you detect a non-zero merger rate, this way you can actually infer the existence of a stochastic background of the sort of weaker events in a roughly 1,000 times less, with 1,000 times less data than it would with the stochastic cross-correlation techniques. So that's an example of going further down the chain in the analysis. Okay. So I'm going to talk a bit about noise models. Duncan showed some of this earlier today. So of course we have these glitch things which can get in and disturb the instrument. They happen quite frequently. In fact, I think these overflow type glitches happen roughly like once an hour or something in O2, something like that. They're pretty common. And there's other smaller glitches and other kinds of glitches that happen frequently. If you think about it, at design sensitivity, a neutron star is going to be in band and LIGO for roughly 20 minutes. We're guaranteed to have some glitches on every neutron star signal we ever see. They might not just always be right in the good stuff right at the end, and they might not be quite so bright. This was actually a SNR 750 glitch on top of an SNR 20-ish signal. So hopefully it won't be like this every time. This actually here is just a movie showing breaking the data up. This is from the LOSC data, the release data. This is just 56 seconds of data surrounding the binary neutron star merger, 8-second segments. And you see that the spectrum sort of fluctuates a bit with time. It's not completely, always the same. So we've got various fluctuations. It's pretty stable, but it moves around a bit. And so the traditional way, if we're talking about the searches, to deal with the non-stationarity, so the non-stationarity really comes in two forms. We've got the glitches, but we've also got just general sort of drifts in sensitivity over time, being sometimes more sensitive, sometimes less. To get around this is locally stationary noise. The way to handle this is just to work with short data segments over which the data is essentially stationary. For the glitches, which also cause non-Gaussianity, there's various vetoes applied to the data. And to estimate the effect of these on the analyses, of course, the time slides where you put in unphysical time delays between the detectors and repeat your analysis and kind of Monte Carlo to find out the impact of these things might have on your analysis. So that's the sort of traditional approach that's used in the searches. Now we're getting into the parameter estimation. We take a Bayesian approach. So something we've been working on is actually modeling everything, including the glitches and the spectrum. Right now, this does not account for these sort of adiabatic drifts in the power spectral density. That's something that we'll get to in the future, we hope. And so, for example, if you want to model a spectrum where you've got the overall sort of smoother component and then a variety of lines, so we just model all of that. So we have a cubic spline, which actually has variable numbers of control points, which are set by a trans-dimensional Markov chain Monte Carlo algorithm. We have lines, which are placed wherever they need to be. Again, it's one of these trans-dimensional things where you don't specify in advance how many lines there are. You just let the data tell you how many lines there are. And so we run this model for the noise. This is now getting integrated into the analyses that we do for the black hole mergers and the neutron star mergers. So we're marginalizing over the spectral model as we actually do the parameter estimation. And of course, we've got the glitches, and we fit them with collections of wavelets and coherently remove them from the data. And as I was mentioning, all of these things are implemented using these transdimensional models. Here's just a simple example, just generated fake data from a polynomial, and then just then fit the polynomial with polynomials of arbitrary degree, and then you have the actual values of each coefficient of the polynomial, then the parameters, and here's a histogram of what we got here, that it preferred a dimension 7 polynomial to fit this data, less so an 8 or 9. It didn't really like 6 or 5 or more, so it actually sort of determines the sort of optimal model dimension to fit the data at the same time as actually fitting it. So we marginalize over models as well as the parameters in the models. And in the case of this Bayes wave algorithm, we're dealing with thousands of parameters, up to thousands of parameters, right? And we actually originally built this algorithm out of the galactic binary subtraction problem for LISA, where we're looking for thousands of sinusoids, essentially. We just switched out sinusoids for wavelets, and then it became this instead. So the same technique. So here's an example. This was actually going all the way back in the data, S5, and here's a case. There was a huge, great glitch in Livingston, and actually this is sort of showing that as the model starts to fit out the glitch, you see that the spectrum in Livingston, which was initially, I'll start that again. Whoop, I've gone the wrong way. Yeah, you see at the beginning here, the spectrum's all messed up because there's this massive glitch that hasn't been subtracted yet. And then as you see as it runs, it eats away at the glitch, finally gets a good model for the glitch. It doesn't take that many iterations really to get there. And then you see that the spectral model settles down to something sensible then as it identifies this huge glitch in the data and subtracts it. And there you see it just modeling everything, all of the lines, the spectrum as it goes along. And then we had a practical example of this with GW 1708-17. As Duncan showed, this was the before in Livingston, and then we have the after once the glitch has been surgically removed in this technique. And in fact, on simulated, if we put simulated neutron star injections in and put glitches over them, we see that it doesn't actually, we nicely remove it without damaging the signal. So this kind of glitch cleaning, we actually even have low latency versions of this that can operate in real time to remove these glitches just on the fly. So maybe we'll start using that. So one other thing that we haven't yet dealt with is these sort of drifts in the spectrum over time. And again, once we start talking neutron stars, where we're talking minutes of data that they are in band, the spectrum is actually slowly changing over that time period. And so it's actually an example of locally stationary noise. And the reason that we do our gravitational wave analysis in the frequency domain is that if you have stationary noise, so if it only depends on the lag between two data points in the time domain and not the actual time, then, as you all know, that means that the noise correlation matrix in the frequency domain is a delta function, right? It's diagonal. And it's really easy to invert a diagonal matrix. If you actually have to invert the full noise correlation matrix, it gets expensive. That's actually what has to be done for pulsar timing. So for pulsar timing, because the analysis, it's not uniformly sampled, it's got all sorts of other complications, the actual correlation matrix actually has to be inverted directly in the time domain. But so what do we do if it's locally stationary? Well, it's almost diagonal in the frequency domain. It goes band diagonal. So you could imagine inverting a band diagonal matrix, which isn't too bad, but it's going to still up the computational cost. In fact, if you go all the way through to the discrete wavelet domain, the locally stationary noise is actually diagonal in a wavelet basis. So this is actually the likelihood that's used by the coherent wave burst algorithm is a discrete wavelet transform, and that's a diagonal matrix then even for locally stationary noise. And so one of the things we could imagine doing is in the same way that we currently fit the spectrum just in frequency, you could imagine instead of just fitting it in frequency this way, we can also fit the spectrum in time. and so using splines going in both directions. And this is an example from LISA where we're guaranteed, no matter how perfect Carsten and his cohorts build the instrument, the galaxy is going to produce a non-stationary, sort of essentially a confusion noise. And so we're going to have to deal with non-stationarity in LISA, even if it's just from the signals, let alone anything that the instrument might throw at us. So I think that this is something we need to investigate. The problem is there's a computational cost. We have all these methods. So this is an in-spiral here. We have these methods such as stationary phase approximation that allow us to have, say, very fast templates in the frequency domain for use in LIGO analyses. But what could we do if we had to calculate things in the wavelet domain? We could possibly use the SPA to actually derive them. We might be able to use some kind of reduced order modeling techniques. You might only calculate the values along the predicted time frequency track. So you don't have to calculate the waveform at 0 most places in the time frequency, so only calculate it where it needs to be calculated. So I think it might be possible to have to shift the entire analysis to a discrete wavelet basis. I think we'll probably need to do that for LISA. And we might start playing with doing that with the LIGO analyses as well for the neutron stars. A little bit on tools of the trade. There's a big machine where we just grind out, we take our inputs, which you write down as the prior and the likelihood, and you have to pop out the answers. Really the key to all of this is how you propose, if you're doing a Markov chain, how do you propose to jump around and stochastically explore your space? So it really comes down to how good are your proposals. So we have recipes where everyone has their own favorite recipe and they all have similar ingredients. You want to sort of have a good guess of what the likelihood looks like. And then you just basically mix all your proposals together and then you check your results. And when your distributions settle down to something stationary, it's the results are ready, and that can take days to weeks depending on how efficient your recipe is. I'm going to skip over some of this stuff. Let's skip all this. This is one that's important. We use this a lot. So we don't just explore the likelihood, we explore the likelihood raised to 1 over some temperature, and that has the effect of making it easier to transition between different modes of the posterior. Often these are multimodal distributions, and this allows us to, it's hard to get Markov chains to crawl all the way down off this hill and find another hill, but this technique, so for example, if I used, this is the mountain range near where I live in Montana, and here's a little Markov chain trying to map out the topography, and it's just crawling around. This one doesn't have any parallel tempering or anything in it, and so it just sort of gets stuck looking around on this mountain and thinks it's a nice mountaintop. It's going to crawl around on it for a while. But if you introduce parallel tempering, and then the white dots are the hot chain, and there's many of them, and then black are the cold chains, you see that they exchange, and it goes off and finds different places, and actually that's the highest mountain in this particular picture here, and you'll see it does jump around and check out all the others if I ran this long enough. So these techniques allow you to kind of get around these multimodal landscapes. Finally, last, I have a whole bunch more slides, but I'll probably stop soon. One of the things you want to do is to check your analyses is what are called posterior predictive checks. It's kind of the fancy name for using frequentist techniques to check that your Bayesian analysis is correct. So, for example, what you might do is inject a whole bunch of signals, run your analysis, and check that you recover the signals in whatever Bayesian credibility interval, that 90% of the time the things that are supposed to be in the 90% credible interval are where they should be, and so this should be a diagonal plot, and so this is just an example showing that on simulated signals you actually get, you're finding the signals in the right part of your probability contours the right fraction of the time, right? So it's like a frequentist test. And other things are, the model that we're using assumes that residuals after we've removed our glitches, after we've modeled the spectrum should be Gaussian noise, and so here's on a log plot what Gaussian noise would be, and here's actually the frequency components plotted against that, you see that indeed it's following a Gaussian distribution, and this is real versus imaginary, and you see no funny correlations in the real and imaginary phases. When you've done things properly, there aren't any such correlations. So you actually want to check that at the end of the day, since your algorithm says subtract everything away until we have Gaussian noise, you want to make sure that your residuals are truly Gaussian, and they are at the end of the day after we've done these. All right, I think I'm out of time. This has already been shown. Most of I've got way too many slides, and luckily this was covered by other speakers, so I actually won't go through all the LIGO examples. So I'll stop there. Thank you.
Exactly on time. Okay.
Could you comment on the best approach to search for things that we are not expecting? Because that would be the next Nobel Prize.
Right. So what I didn't mention is, I mentioned it sort of in passing on a couple of occasions there, and we don't actually have a dedicated talk, I don't think, in the conference on this, but in addition to the continuous waves, the template-based searches, there's also the burst searches, and a couple of them I mentioned, they're mostly wavelet-based. Probably the main online search that is the most, that has the richest modeling is coherent wave burst, which is uses a discrete wavelet transform. There's another one called Lau inference burst, which uses single wavelets, and then a more expensive sort of follow-up that does full reconstructions, which you've actually seen in a lot of those LIGO papers. Those wavelet reconstructions are done using this Bayes wave algorithm, which I was showing mostly for its glitch removal, but that's also it reconstructs the gravitational wave signals in the same way, right? So we're able to reconstruct, supernova waveforms. We're able to reconstruct post-merger signals. We put a paper out recently, a group of us, on reconstructing the post-merger signal from neutron stars. And then, of course, the great hope is that there will be things that not only are poorly modeled currently, but things that are completely unexpected. And we have ways to then reconstruct those, and we get the waveforms, and then you can kind of infer things like the duration of the signal, its time frequency evolution, and so then you can start playing that detective game of what created that signal, right? A bit like going on right now with fast radio bursts, where you get this mystery and then you've got to do your detective work. So I should also say that as of the published detections so far, the burst group only missed one, and that was the Boxing Day event. We got every other signal, right? I'm not saying that templates aren't important, they're great, and that's how we get all the parameters about the systems, but actually in terms of detection, we've only missed one, and the interesting thing is if you take the Boxing Day event, which was a little bit lower mass system, but at that SNR, and you inject that signal, like 95% of the times the burst searchers find it. It just was just a bad noise realization. We just got unlucky. That is not one that's out of reach. That's totally within our abilities to detect. We only got like a little bite on it. It was just a bad luck one. But anyway, so the burst searchers are pretty good. And so I think I'm feeling confident about our chances to detect completely unexpected things.
And in the context of burst, I can talk tomorrow about superconducting.
So, my question relates to timescales for these kind of analysis. So in 03, the LVC promises to have alerts out in a few minutes, which means that you can do the sky reconstruction map and a distance estimate and inclination and all that stuff within minutes. Is there a barrier from a technical point of view for providing things like what you're showing here, for example, on those kind of timescales from even in a very rough sense of starting to map out the parameter space to make statements like, there's non-zero spin or something like that, or is that something that takes weeks and weeks to get?
I think that there are people that have working on that. There are ways to do a cruder, quicker kind of mapping, and in fact, there are several efforts within LIGO, some of them published, some groups in LIGO that are actually looking at considerably faster methods. There's all sorts of tricks for how you can, for example, Chris Pankau, who's working in Vicky's group, and I guess that's with Richard O'Shaughnessy and whatever, they have some methods that are essentially a way, the computationally expensive part is calculating the likelihood, but there's some tricks for how you can do that much more rapidly. So I think that I think it's possible with some smart, implementations that we could get at least good, pretty rough, but mappings out much more in like minute-type latencies rather than days latencies. So a bit like our sky maps, how they get progressively better, but sort of ever improving. So I think there's definitely a lot of work going on more rapid production of.
Since this is in connection to this, it's not since my group was mentioned. What can be provided in minutes is really what Duncan showed in his talk, which was that page where the chirp mass, the total mass, the distance, the sky, even the sky map takes a little bit of time. Like for the double neutron star, we didn't have it available within minutes. The effort Neil is referring to, which is ongoing, really led by a postdoc in my group and Richard O'Shaughnessy at RIT, is really not production level right now, and it doesn't deliver results in minutes, results that even we can trust. And for most of our, for all of our events right now, we can tell that the spin is non-zero. So we just don't have these statements delivered even for us in minutes.
Vicky's talking about current reality. I was thinking longer term of what is conceivably possible. Yeah.
So,
right.
So I have maybe more confidence in LIGO and Virgo than Vicky does, because one of the things that's released in 02 was the probability that one of the objects is a neutron star. And to get that, you need a preliminary mass and spin estimate that you then feed into Francesco Panarella's mapping to, what's the probability that you'll see something that's torn apart that there's low mass here. So I think I would side with Neil and say I think that LIGO and Virgo, if they wanted to, could get preliminary mass and spin estimates out very quickly that they could then refine later.
I disagree with that. We make spin assumptions and we can make probability, we can give probabilities for masses, but we cannot give estimates for spins.
Thank you. Okay, so I found this business about the adiabatically varying noise interesting, but I didn't understand the procedure. Do you just divide the data into chunks and assume that each is an independent noise realization, or do you assume there is some smooth variation?
Well, the current approach, which is used in the analyses, for example, a stochastic analysis, is the data is broken up into small pieces where it is, to a good approximation, stationary over that amount of time, right? So some number of seconds. And the time scale on which it's stationary actually varies. So there are some times when it's really just sitting there beautifully quiet and the spectrum will just sit very, very nice and stable, and the other times where it's sort of moving a bit more. But yeah, so this sort of locally stationary, you can literally break it up into small pieces. What I'm talking about is when we want to deal with a very long signal over time spans where we know it's going to be varying, there it would actually be modeling the adiabatic change in that noise floor rather than just breaking it up into little pieces.
But even when you break it up, you might have a bias where succeeding times are not completely independent.
That's right.
They should look somewhat similar. And you could imagine putting that extra prior
into the next
fitting.
Absolutely.
Yeah. But you don't do that.
No, not right now.
Okay, last question.
So you've mentioned that you can measure the merger rate of gravitational wave events using sub-threshold events, and how does that change the actual value of the merger rate for black hole mergers?
I don't know what the answer is right now. I mean, that was a theoretical paper. This hasn't been implemented. There was actually another very nice paper from several years earlier by Messinger and Veach that talk about using, they give like a toy model showing how using sub-threshold events allows you to get a considerably more accurate and unbiased estimate of like merger rates and things like that. And there was a similar paper that had a collection of authors, including Will Farr and several others. So this idea of using, not just the cream of the crop, but going down is sort of out there and starting to get looked at being actually used, but we haven't necessarily fully implemented all of that yet into the analyses in LIGO, but it's happening. It's just taking, you know, a little while to get there, but moving in that direction.
About the efficiency of bursts to detect unknown signals, isn't there a time limit? I mean, unless you have energy focused in time and frequency, it'll be very difficult. I believe the current search is around 1 second or a few seconds, correct? There are
No,
also
there's
long duration burst searches.
There's long duration
but
burst
they're not
searches.
as sensitive as.
Well, it basically just comes down to how do you concentrate, you know, the idea is you want to concentrate the signal into as few pixels, if you like, in whatever
Exactly.
basis
Yeah.
you're looking at. And so these longer duration searches essentially can look to concentrate into different kinds of mappings than the sorts of wavelets that are, say, optimal for a, you know, a black hole. So these techniques, you know, at one extreme you go across to actually just taking segments of data and essentially just doing cross correlations on them, but there's other more sophisticated things. So the long duration burst searches, you know, have you know, decent sensitivities to, and that's a very active area that's been coming on the last year. So it doesn't have to be a real thump. I mean, we can detect, you know, certain neutron star signals, like the first one. It was nice and bright.
That's correct, but it's always a question of sensitivity.
Right.
Right, I mean, anyway.
Okay, let's thank Neil again.